This conference will now be recorded.
Hello everyone. So we are continuing with chemical properties of alkanes and reaction with steam, which is number 8. This was already complete, and next we have pyrolysis. With that, we just started it in the last class, but we are not able to finish it. So first I will finish it, and then we'll go to the next topic, which is alkene. But before that, we'll also see the uses of alkane. So pyrolysis. Pyrolysis, another name, is also cracking. It is a process by which solid or liquid undergoes thermal degradation. Because if you break this word, pyro means fire and lysis means disintegration. So using heat, when we disintegrate some large molecule to smaller molecules, smaller volatile molecules in inert atmosphere, then it is called pyrolysis or cracking. In the absence of air, when alkane vapors are passed through red hot metal under a pressure of 6 to 7 atmosphere in presence or absence of catalyst, there will be breakdown to simpler hydrocarbon units. Now this process involves breaking of carbon-carbon bond and carbon-hydrogen bond, and the mechanism is free radical mechanism. Now some more important points related to pyrolysis. The type of products that we will get from pyrolysis, there is nothing fixed rule about it. It depends upon the nature of the alkane, temperature, pressure, and presence or absence of catalyst. So it is basically dependent on the reaction condition. And it will occur very easily if the molecular weight is high for the alkane, and also if there is increase in branching in the alkanes, then this process will be very good. Fine. So these are the important points. Now look at these examples. Here we have C4H10, which is butane at 973 Kelvin. There is formation of some simpler units, and these simpler units, as you can see, there is ethane, there is ethene, C2H6, C2H4, then methane, propene. Propene is also there. It is not that always you will get alkane. You can also get alkene. From the formula, you will be able to understand. C2H6, which is the formula for alkene. Number of hydrogens, double of number of carbon. And it is written also here. You will be able to understand from the name also, and as well as the formula. Next, C6H14, that means it is hexane 773 Kelvin. And here also we are getting alkene, as well as there is formation of alkane. So there is no such fixed rule that which we will get. There will be actually mixture of simpler units. Then we have C8H8, carbon number total 8, and this is also alkane. We are getting in hexane, ethene, butane, ethene, methane, and also carbon atom. Now this type of cracking, it has some application in petroleum industry, very important application. We can prepare oil gas starting from kerosene oil and petrol gas starting from petrol, and it is based upon the process of pyrolysis. Fine. So this is the application. Now for example, if we consider dodecan means total number of carbon is 12. So if it is 12, then hydrogen will be 12 into 2, 24 plus 2. So it will be 26. And from this we get, and remember this dodecan is constituent of kerosene oil. So we are just seeing one of the example how it is playing important role in petroleum industry. So dodecan, which is important constituent of kerosene oil, when we are heating it at 973 under the catalytic action of PT, PD or nickel. So any of this metal if we take, we get mixture of heptane, that means there will be formation of C7H16, pentene, that means C5H10, and there will be some other products. Fine. So this is pyrolysis. Now we have finished all the reactions related, that is chemical properties of alkanes, and based on that we have a problem here, and the problem is saying that few reactions of alkanes you can see here. A, B, C and D, total 4 reactions are there. And it is asking that identify the name of the reaction which is not correctly matched with the reaction. So some names are also given for each of these options. A, it is mentioned as isomerization. For B, it is mentioned as pyrolysis, then controlled oxidation, and then nitration. Now you have to find in which case it is not a correct name. So you have to recognize the reaction, right? That is the question is all about. Here the first option A, we have the molecule butane, linear chain butane in presence of aluminium chloride and HCl, which is hydrochloric acid. So this is Lewis acid catalyst in presence of acidic condition. If you look at the product, you can easily understand it is basically isomerization. Starting from N-butane, now you are getting another molecule where total number of carbon hydrogen is still same, only the branching you are getting. And the parent chain, there is total 3 carbon. Here we have 4 carbon because we have one branching. So it is isomerization. And this is correctly, the name is correctly given. So it cannot be correct option. Come to the next one, C6H14. It is alkane, high temperature. We are getting some smaller units, C4H8, C2H6. That means you are getting C4H8 is some alkene, butene, and C2H6 is ethane. So this is pyrolysis. We just ended the process pyrolysis. So we know very well what is pyrolysis. Then option C, methane reacting with oxygen. And look at this. This is complete oxidation because in the left hand side you have 1 carbon. Now you are getting 1 CO2. You have 4 hydrogen and now you have 2 H2O. So all the 4 hydrogens are in the form of now water. And it is mentioned as controlled oxidation, but it is not controlled oxidation because CH4 is completely converted to CO2 and H2O. And when it happens, remember the reaction? The reaction is combustion. It is not controlled oxidation. It is combustion. It is full oxidation. So this is actually the correct option. The name is not correctly given. And the next one, which is mentioned as nitration, this is obviously correct because here CH4, one of the carbon hydrogen bond, now it is replaced by carbon NO2 bond. And rest of the 3 carbon hydrogen bonds are still there, so there is no change. This is obviously nitration. So only the third one, it is not correctly matched. It is controlled, no, it is not controlled oxidation. It is combustion. That is the correct name we should use for this reaction. Which of the following is correct matching regarding controlled oxidation of alkane? Now you can see some examples of controlled oxidation. Option C in the previous question is not controlled oxidation, right? So in controlled oxidation that we have finished in the last class, you have seen that different types of metal catalyst or metal related catalyst, maybe some oxide of metal, it may be some other compounds of metal. So different types of metal catalyst, metal related catalyst, and you have alkane, depending on what catalyst you have taken and also the reaction condition, you get different types of products. Column 1, column 2, we have to match. In column 1, we have tertiary butyl group. See, the molecule is like this. 3 methyl groups are attached to carbon and there is one CH. Now this H is 3 degree in nature because the carbon with which this hydrogen is attached, that carbon is also attached to 3 carbon. So this is 3 degree and 3 degree hydrogen, its oxidation is only possible in presence of KMnO4. But what is the product we get? That is the important point. The product we get is simply the replacement of H with OH, and that molecule you can find in 2. So A will be matching with 2, correct? Then methane in presence of oxygen, copper catalyst, high pressure, 523 Kelvin. When we simply use copper metal, the reaction was mentioned if you consider that particular slide where I have discussed control oxidation of alkane. There you can check. You will find it is mentioned like this, that the alkane is passed to the copper tube. And when we do so, we get methyl alcohol. So it is matching with 3. Third one is again oxygen we have taken because all these are basic in presence of oxygen. There is no doubt about it. But we are just changing the reaction condition. That is the difference we are making. In option C, now we have taken the catalyst molybdenum related, and this is molybdenum oxide, MO2O3. So in presence of this type of oxides, what happens? Methane is converted to aldehyde. So methane will be converted to this one, 4. And the last one, we are using a very special type of catalyst. You can see manganese acetate. 2 acetate group attached to manganese in presence of oxygen, and in this case, we get ACOOH. So the last one will be matching with 1 in column 2, formic acid. Fine. So these are the different types of control oxidation. Uses of alkane. So this will be the last topic related to alkane. Then we'll start alkene. And first we'll see the properties, that is introduction for alkene, then its structure, nomenclature, isomerism, everything. So uses of alkane, some of these uses you have already seen, but here we will just summarize all the points. Natural gas, you have heard this. Hydrocarbon mixture, it is nothing but hydrocarbon mixture, but especially there is presence of methane and ethane. It is used for heating, cooking, fuel for vehicles, electricity generation, so many different types of applications. Then liquid petroleum gas, in short we call it LPG. It is mixture of propane and butane, both of them are alkane. Now this gas we use for domestic cooking purpose. Now LPG itself is odorless, because you know these are odorless, and hence to just to for safety purpose, if there is some leakage, there may be some accident, just to for the safety purpose there is some compound added which has some specific smell. This compound LPG propane butane mixture, they are not having any specific smells, but if there is no smell, if there is leakage occurring, we will not be able to understand. So just to ensure that some leakage is occurring, we should add something which is having some specific smell, and that is ethyl mercaptan. Okay. Then gasoline, that is also complex mixture of many hydrocarbons used as a fuel for internal combustion engine. So all these terms basically you are seeing here, they are basically mixture of hydrocarbons. Now we have some methane related points. Methane in form of natural gas that is used in running scooter, cars, buses. So this is also a point that we have already seen as in the first point. Then methane has used for carbon black preparation, and that is important in printing inks, paints, automobile tires. Methane used for manufacturing high halogen containing compounds. Now this application you have seen in chemical properties under the heading of chemical properties, where we have that is, remember the reaction halogenation, where some carbon hydrogen bonds are replaced by carbon halogen bond. So if you start from methane, if you replace some carbon hydrogen bond with CX, suppose you have replaced two carbon hydrogen bonds with two chlorine atom, what you will get? You will get CH2Cl2, dichloromethane. Then you have replaced three carbon hydrogen with three chlorine atom. What you will get? You will get CHCl3, right? Catalytic oxidation of alkane gives aldehyde alcohols carboxylic acid. Remember the last problem in the previous slide we have discussed controlled oxidation, and that point is mentioned here as application purpose, uses of alkenes. So depending on what type of catalyst you take, what type of reaction conditions you have, you will get alcohol, aldehyde or carboxylic acids. Higher alkanes in form of gasoline, kerosene oil, diesel, lubricating oil, paraffin wax. So all these are having very wide use in industry. So alkane is finished. Next we will start alkenes. So alkenes are unsaturated hydrocarbons containing one or more CC double bond. So at least one CC double bond must be there. Otherwise, how we can call it alkene? Okay. Now just try to understand. C double bond C. So the first member, it has to be at least two carbon must be there. For alkane, you can start from CH4, but when it is C double bond C, there must be two carbon at least. So that is why the first, that is the simplest member possible, is this one, right? Now in this case, number of hydrogens are decreased because carbon, for one of the valency of carbon, it is fulfilled by making bond with another carbon, and this bond is pi bond. But whatever it is, now the requirement of hydrogen is less compared to alkane. So same type of compound, that is same. What I mean by same is, if you take again two carbon, but suppose now you do not have any CC double bond, you just have single bonds like this. So just compare. Here you have three hydrogen. So per two carbon, here we need 6 hydrogen to satisfy the valency. But when you have double bond, the requirement of hydrogen is less. And that is the reason now the general formula will change. In case of alkane, what we know, the general formula CnH2n plus 2. But in this case, it will be CnH2n. Simply the double. This plus 2 is not required here. But remember, it is only for those compounds where you have only one double bond. Because if you have more than one double bond, suppose I am having this compound H2C, C, then one single bond, then another double. Now, if maintaining 4 carbon, let me write 4 carbon again, but now I have only one double bond. Put the hydrogens. So in this case, suppose this is A, this is B. So when it is A, you will see this formula you will not find here. But for B, C4, what you expect? Cn, 2n means it should be 8. And here it is 8. 2, 1, 3, then 4, 5, 6, 7, 8. But here you will not find that because now it is not 1 CC double. So C4, 1, 2, 3, 4, 5, 6. So it is 6, is C4H6. So as you have used another double bond, so obviously the requirement of hydrogen is even less, right? So if there is 1 CC double bond in alkene, they will have 2 hydrogen atoms less than the corresponding alkene. So corresponding means here you have 2 carbon, this is also 2 carbon, but you do not have any double bond. So when you compare the general formula, now the requirement of hydrogen is less. And this n value is obviously greater than 1, cannot be less than 1. But this formula is only for provided you have 1 CC double bond. The aliphatic unsaturated hydrocarbon, sometimes there may be 2 CC double bond or 3 CC double bonds. In those cases, what will be the name? Now the name is not alkene, now it is alkadiene. Suppose you have 4 carbon and 2 double bonds. Just take this example. So what should be the name? It should be butadiene. And also if you want to mention positions, this is 1 carbon, 2 carbon, 3 carbon, 4 carbon. So the double bond positions are number 1 and 3. So it should be 1,3-butadiene. But general name is alkadiene. Just we use the term alkene when you use it when there is 1 CC double bond. But alkadiene means now it is butadiene or hexadiene, pentadiene, like this. And you can also have 3 double bonds. In that case, it will be alkatriene. They are not found in crude oil in very large quantities, but are produced by cracking of alkanes. Remember, in the cracking of alkanes, that reaction we have seen in today's class. In the first slide, there you have seen some examples of alkane where after pyrolysis, one of the product is also alkene. So that may be a source. You can treat it as a source to get alkene, right? They are having another name which is olefin, because in Latin the meaning of this word is oil maker. Now why we are calling it oil maker or olefin? Because the first member means ethylene. This compound is called ethylene or ethene, C4H8. It combines with chlorine or bromine and it forms an oily liquid. So because of this first member only, they are also having another name which is olefin. They are important in chemical industry for the manufacture of plastic and many other chemicals to be used as fuels. So in a polymer chapter, if you read there, you will see the applications of these double bonds, because the monomer that we use for the preparation of polymer, monomers, many monomers, you will see examples where CC double bonds are present. So that you can consider as example of that is use of alkenes. Okay, manufacture of plastic, I mean polymer. Now we have the next topic, structure of CC double bond. Now if you are thinking we have not discussed anything special about the structure of alkane, but now the difference is you have one pi bond also extra, so that we need to understand. And because of this presence of pi bond, the properties of alkenes completely changed compared to alkanes, right? Now to understand CC double bond, there is one pi bond, there is one sigma bond, you have to understand the hybridization. Carbon, it is 1s2, 2s2, right? If I only consider the valence share, it is 2s2, 2p2. So in 2s you have 2 electron and in 2p you have 2 electron, but I am not writing 2 electron because in excited state the electron will be shifted to 2p. So now it looks like this. If there is sp2 hybridization, that means one s orbital and two p orbital together, it will make sp2, sp2, sp2. So you have taken one s and you have taken two p and you are mixing, you are getting 3sp2. Now this p is not hybridized, it is unhybridized. Okay, this 3sp2 will be used for bond formation, for sigma bond formation. So you are getting one sigma, second sigma, third sigma. So when you have cc double bonds, just take the simplest example, we will take ethylene. Now consider each carbon. So this is one sigma bond, this is one sigma bond, this is one sigma bond, and same is also true for the second carbon. Now all the sigma bonds are made by sp2 overlap. So carbon will use its sp2 to make cc bond with sp2 of carbon. This is single bond, okay? And hydrogen will use its 1s to with sp2 of carbon, and all these are basically head-on overlap. So s orbital for hydrogen I can write like this, and for carbon this is head-on overlap, and that is why it is sigma bond. Fine. Now there is one p orbital left, and that p orbital, there is also one electron, and this electron will be utilized for pi bond formation. Remember, whenever you have pi bond, the electron that is always in unhybridized p. This cannot be from hybridized orbital. And this p orbital, there will be sidewise overlap like this. So this type of sidewise overlap, obviously compared to a sigma bond, which is head-on overlap, it is very strong. But unlike sigma bond, now it is sidewise overlap, so it is not so strong, and that is the reason pi bonds are weak. So cc double bond in alkenes consists of one strong carbon-carbon sigma bond. That is, one strong means we are just focusing on cc double bond. So in this cc bond, one is sigma, one is pi. Head-on overlapping of 2 sp2, and then we are getting sigma. There is also one weak pi formed by lateral or sidewise overlapping of the two unhybridized 2p orbital of carbon, and this is the reason this will be weak. To have effective overlap in pi bond, the p orbitals must be relatively closer to each other. So these two p orbitals, they must be close to each other, because closer they are, more effective will be the overlapping, and that is the reason if you compare cc double bond, just compare with cc single bond. In case of double bond, the length is 134 picometer, but in case of cc single bond, it is now 154 picometer. And when I'm saying cc double bond length and cc single bond length, don't think that it is these values are for ethylene and alkane. It is basically the average value, because compound to compound, this value may differ slightly. Suppose you have cc double bond in ethylene, you have cc double bond in some other compound. Suppose you have hexene. So the double bond length in hexene and the double bond length in ethylene, it may not be same. So this value is just average value of different types of cc double bonds. If you take the average, this is the value, and that is also true for the cc single bond, right? So this is the reason why it is shorter compared to cc single bond, right? Now alkenes, because of presence of these loosely held electrons in pi bond, now because of this presence of loosely held pi bonds, loosely held electrons in pi bonds, they can be a very good nucleophile. So alkene, they can be nucleophile. When we first learned about nucleophile in the chapter unit 12, that is the basics of organic chemistry, there we have first learned this term nucleophile, electrophile. There also you have seen the examples of the pi bond as nucleophiles, but now you can understand the reason why they can act as nucleophiles. So when you have cc double bond, just take the example of ethylene, that is the simplest one. So these electrons that are involved here, they are basically very loosely held. So these electrons, if you have in the medium, if you have any good electrophile, this nucleophile, the electrons can be easily attracted to this E plus, right? So in presence of electrophile, that is, they are readily attacked by the electrophile. Next, one more information. Bond dissociation energy. This is obviously the average bond dissociation energy, just like the bond length, which is also average. So for energy also it will be average. Look at this value, 611 kilojoule per mole. And this value is obviously greater than the BDE, average BDE of CC bond, which is 350. It is almost half amount. Now, don't think that pi bonds are loosely held, then why it is strong? It is true they are loosely held. But remember, when you are breaking CC double bond, you have to break two bonds actually. But here you are just breaking one bond. It is true there is pi bond, which is loosely held. But you have to break pi. You have to break sigma also. But in this case, you are just breaking sigma. So obviously it will require less energy. Okay. And one more important point. Alkanes, we know they are very inert. They do not want to take part in reaction. But compared to alkene, that is where you have double bonds, they are more, that is, they can easily take part in reaction. And the reason is this loosely held electrons in pi bond. This bond you can easily break. Now, this amount of energy is required only when you are completely breaking it. But when you have some CC double bond and you are just breaking only the pi bond, not the sigma bond. Sigma bond is still there. Pi bond is gone. And instead of pi bond, rest of the valencies, suppose there are some groups, you have broken this pi bond, and suppose in that place, you have some other bonds with some other molecule. Simply take hydrogen. So here you are breaking only the pi bond, not the sigma bond. You are not breaking the full double bond. When you are breaking the both the bonds, then 611 kilojoule per mole is required. But if you are breaking only the pi bond, this is not the energy required. Okay. Now we have a question related to this. Statement 1 is saying presence of weaker pi bonds make alkenes less stable than alkanes. Now less stable means what? They are more reactive. Now this is obviously true. They are more reactive. Less stable means more reactive. Stable means inert nature. This is true. Come to the second statement. Strength of double bond is greater than that of carbon-carbon single bond. And that we have just seen. This is 611 average value, kilojoule per mole. This is 3550. So this is also true, isn't it? Though these two statements at a first glance seems contradictory, that we are saying presence of weaker bonds makes alkene less stable, they are more reactive, then how the double bonds is having more energy, then how it can be more reactive. But remember, when we are saying more reactive, we are just breaking pi bond. We are not disturbing the sigma bond. When you are completely breaking both the bond, then 611. But when you are breaking only the pi bond, suppose you are breaking this, not this one, this is still intact, then this is not the energy we required. This is not equal to 6,1. Okay. So don't think that these two statements are contradictory. Both are actually true. Option A is the correct option. Nomenclature of alkenes. So we have already seen that compounds can have 2 CC double bonds or 3 CC double bonds. So they will be diene and triene. Now we will see some examples of different types of diene. So under diene category, there is different types of possibilities. So these, look at the first possibility, number 1, which is called cumulated. Another name for this particular class of compounds is allenes. So here double bonds are basically adjacent, isn't it? They are adjacent to each other. And look at this bond here. These two bonds, there may be any substituents. This is the general way we are trying to see the structure. So these two bonds, if they are on the plane of the screen, and if you consider now this terminal bond, this, whatever is the substituents here, suppose A or B, then the Ca bond is back of the screen and Cb bond is towards us. Now why it is so? Because if you have considered this pi bond here, now this pi bond, suppose it is on the plane of the screen, but when the middle carbon is using its pi orbital, the another unhybridized P, which is present in the middle carbon, that will be overlapping with the second carbon's pi in this way. Now these two pi, they are actually perpendicular to each other, and because of this type of 90-degree nature between these two pi bonds plane, the substituents at the two terminal positions, they are also like this. So substituents, if I'm writing at AB, this ACB, if these three atoms in the plane of on the plane of the screen, these ABC, they will be perpendicular, right? So that is details of halides. That is not our topic to discuss. So this is cumulated diene. Then the second type, okay, under this we have this example, simplest example, propadiene, because in the longest chain you have three carbon, that is what is prop, and it will end with prop, but we are just removing propane. Ne remove, just add di. So this is propadiene. Then the second type we have conjugated. Now try to understand the difference with the previous one. What is the difference between cumulated and conjugated? So in conjugated, between two double bonds, now you have one cis single bond. And this is the general way to represent. There may be any substituents, but if you consider substituents like this, where you have one hydrogen here, hydrogen. So now it is, we are calling it 1,3-pentadiene, because longest chain total 5 carbon, numbering will start from here 1, 2, 3, 4, 5. So at one position double bond, at three position double bond. That is why the name is 1,3-pentadiene. Okay. And one more example also we can take under cumulated, which is CH3, CH. Though if you consider stereochemistry, these two bonds and these terminal bonds, they will be perpendicular to each other, but just neglect it. And remember here, this carbon is sp2, middle carbon is sp, and this is sp2. And middle carbon has to be sp, because when it is sp, that means it is using out of 3p orbital, only one p orbital. And rest of the two unhybridized p orbital, that will be used for pi bond formation, because only the middle carbon is having two pi bond. One in the left hand side, another one in the right hand side, right? So conjugated we have understood, and now the next one is isolated. What is the difference with conjugated? In conjugated, between two double bonds, you have only one single bond. But now the double bonds are separated by more than one single bond. They are separated by one single bond only. But now this CH2 is written as N, where N is some integer. Now, if you simply consider N value as 1, the simplest structure possible is 1,4-pentadiene. So numbering will start, this is symmetry, you can start from any side. So the double bonds position as number at number 1, at number 4. So that is why the name is 1,4-pentadiene. You can also increase the value N. So in that case, it will be like this. So now the value is, N value is 2. N value, when 1, that means 2 cc single bonds are present in between two double bonds. When N value is 2, now 4 cc double bonds are present. Dienes are made by replacing N suffix, that is, we are talking about nomenclature. So N from the alkane will be removed, and in that place you have to add adiene. So just take example of propane. So in propane, you are removing the term ANE. Instead, you are putting adiene. And identifying the position of double bonds following rules of first point of difference that we have in detail discussed in a previous unit. So we are not going into that. We'll just see some nomenclature examples applying the rules that we have already learned before. So identifying the position of the double bonds and following the rule of first point of difference. So just take this example. What will be the name for this molecule? So let me start numbering. Here, this is double bond. This is another double bond. 1, 2, 3, 4, 5. So 5 carbon chain. Position of double bonds. This is symmetric. Position of double bonds is 2 and 3. So the name will be 2,3 pentadiene. Okay. Now we will discuss some examples that is under some examples of nomenclature, and obviously this is the nomenclature for alkenes. So first we will draw some structure. So in this molecule we have 2 double bonds, right? Now the first thing that you have to do is you have to choose the, okay, let me draw all the molecules first, because I am using a black color for it, and when I will now do numbering I will be using some other color. So this is the second molecule that we have to do nomenclature. This is the third one. You can also try and then see whether it is matching or not. Okay. So for the first compound, you have to start numbering from that side according to rule of first point of difference. Suppose if you are choosing numbering from the left hand side, the first double bond will get position number 2, and then 2, 3, 4, 5. So it will be 2 and 5. But if you start from the right hand side, the number you will get 1 and 4. So that is why this will be the correct way to numbering. So total 6 carbon chain you have, and you have one propyl substituent at 4 position. This is the propyl substituent, and the name will be I'm writing it down. So it will be continued. There should not be any gap. Fine. Now the next one here, numbering will start from which side? That is the question. If you are starting from this side, suppose 1, 2, 3, 4. So in this case, what will happen? The double bond is getting position number 2, but halogen is getting position number 4. But suppose if you are doing the reverse, if you are starting the numbering like this, 1, 2, 3, 4. Now in that case, halogen is getting number 1 and double bond is getting again number 2. So in both cases, you are getting same double bond number, but in the second case, halogen is also getting lesser number. So that is why the blue numbering will be the correct one, right? So name will be longest chain. We have total 1, 2, 3, 4, and double bonds position is 2, butene. Okay. Now the next one. Obviously, you have to give priority to the double bond, because now if you start numbering from the chlorine side, double bond will get very large number. That is obviously not correct way to do. So it will be 2, numbering will be from this side. Total 7 carbon, and at 3 position you have propyl substituent, and at 7 position you have chloro substituent, right? 1, 2, 3, 4, 5, 6, 7. Okay. 7 chloro, and at 3 position we have propyl. So chloro will be first because C comes before P, and position of double bond is 1. So that is why it will be 1 hexene. The next one, choose numbering. Now obviously it will be starting from here, 1, 2. Now if we move in the left hand side, there is 3 carbon. In the right hand side also 3 carbon, but remember in the right hand side you will get 1 substituent. So that is why this will be the correct position for numbering. So I'm moving towards right hand side because of this ethyl substituent. Because if you are doing the numbering in the left hand side, then what will happen? We will not get proper substituent, right? So here we have ethyl substituent and we have propyl substituent. Two substituents are there. So propyl, 1, 2, 3, and ethyl. Now E will come before P. So that is why ethyl should be written first. So at 4 position you have ethyl. Right? Okay, so we are done with all the nomenclature of alkenes. After nomenclature, isomerism of alkenes. Now, what type of isomerism mainly we observe in case of alkenes? It is structural isomerism. Under structural, you will get chain, you will get position. Then ring chain isomerism is possible, and geometrical isomerism, which is very, very important because it is exclusive only for alkenes. So that is, it is so important. Structure, the first one. So structural isomerism is possible only from the third member. Now the first member under alkene, you know, it is C2H4. The second member is C3H6. The third member is C4H8. Because you cannot have first member with one carbon, right? So C4H8 is the third member. Only from this member you can have structural isomerism, because when you have propene, this one, now with propene you cannot make any changes, you cannot have any structural isomers. It is not possible. It is possible only from C4H8. So we will see some structures under C4H8. So all these are C4H8. But what is the difference? If you consider 1 and 2, the relationship 1 and 2 are basically position isomers of butene. Because in the first case, the position of double bond is at 2 position, right? And sorry, it will be 2 butene. This is 1 butene. And in the case of 2, position of double bond is 1. So that is why position of double bond is different. That is why they are related as position isomers. But if you consider the relationship of 1 and 3, now 1 and 3, if you compare the parent chain, here it is 4 carbon, but here it is 3 carbon, isn't it? So numbering will start 1, 2, 3. 2 position there is methyl group and it is 1 propene. So as there is parent chain itself is different and you are having some branching, that is a chain itself is different. So that is why these two are related to each other as chain isomer. And the relationship of 2 and 3, that is also chain isomer, because in 2 also you have 4 carbon in the parent chain, but in 3 you have 3 carbon in the parent chain with 1 methyl substituent, right? So after structural isomerism, the next one is ring chain isomerism. So ring chain isomerism means one structure will be having some ring structure, another one is chain. But remember, it is when you will have the ring structure, there will not be any double bond. So simplest, that is a first ring chain isomerism is possible is with this one. Ring chain isomerism possible for alkenes, and alkene will be playing the chain part and the ring part will be from cycloalkane. So here I have drawn cyclopropane, right? So the formula is C3H6. Now remember, cycloalkane and alkene, these two will have same type of formula. Normal alkane, what we know, it is CnH2n plus 2, right? But when it is cycloalkane, now it is CnH2n. Why? Because the two terminals are connected. So obviously the requirement of hydrogen is now less. But this formula, it is also same for alkene. So that is the reason if you take alkene 3 carbon and if you take cycloalkane 3 carbon, these two will have same formula. That means number of carbon hydrogen same, and that is why they can form some ring chain isomer. So here we have propene. This is also C3H6. This is also C3H6, right? So both are having same formula but ring chain. So this is possible. that is ring chain isomerism is possible between these two. Similarly, I can take C4H8 cyclobutane, but now in this case you will have, you can take 1 butene, 2 butene, whatever you take. This C4H8, this is also C4H8. Okay, so these two are related to see this cyclobutane by ring chain isomerism relationship. Geometrical isomerism, the third isomer, is very important. Now, why this isomerism arises? The reason is rotation about a CC double bond is restricted. We know CC single bond. We have also seen some rotamers. Remember, the conformational isomerism possible in case of alkane, but that is possible because rotation around CC single bond is easy. You can easily do it. But rotation about CC double bond is strongly hindered and restricted. Why? Because when it is CC double bond, you not only have sigma bond, but you also have pi bond. And for pi bond, both the carbon, these two orbitals, they must be in the same plane. But if you simply rotate it, one orbital, now it will be somewhere here. Pi bond is not possible. So you have to break it. It is energy requiring process. So that is the reason CC double bonds rotation is restricted. And that is the reason, as the rotation is restricted, whenever you will have some CC double bond and you will have some substituent, suppose X, Y, A, B, whatever, they will have some fixed positions. Now, depending on their positions, you can have different types of isomers. Okay. Now, what type of isomerism is possible? Suppose simply take CH3, CH double bond, CHH. Now, in this case, geometrical isomerism is not possible. Why? Because in the right hand side, you have two similar groups. So even if you change these two hydrogens, it doesn't make, it will again be same thing. If you change CH3 and H, it will be same molecule again. So here it is not possible. Similarly, if you take a molecule where you have two same groups on one side, again two same groups on the other side, this is also not possible. But so the main point is you must have two different groups both sides. Then only geometrical isomerism possible. So here larger groups compared to that, just focus on carbon number 1 first. In carbon number 1, this is having more priority than H. Now focus on carbon number 2, CH3 having more priority. Now both the higher priority group, they are on the same side. And that is the reason it will be cis isomer and the trans isomer will be. Now the two higher groups, they are on the opposite side. That is the reason it will be trans. And remember, in these cases, cis-trans isomerism not possible because you have two similar groups attached to carbon, whether it is methyl or any other alkyl group or hydrogen. But similar groups attached to carbon, then cis-trans is not possible. Now, after cis-trans, sometimes what happens, cis-trans isomerism is not efficient. It is not enough. It is not sufficient. When it is not sufficient, when there are more than two different substituents. So in the previous examples, you just have two substituents, one methyl group, one H. You do not have any third type. But now look at these two molecules. They are having third type because here you have Cl, you have OMe group, you have CH2, CH3 group, you have H. So all the four groups are different. Even if you have three different groups, then also cis-trans you will have some problem. What three different group means? Suppose you have two Cl, one OMe, one CH2 CH3. Then also cis-trans will be difficult. So it is not sufficient when there are more than two different substituents. That is three different substituents, it is not possible. So in case of first molecule, because similar groups both sides you cannot compare, right? In the previous case system, what we have said that two similar groups are on the same side, two similar groups are on the double opposite side, but that now you cannot say. Now among Cl and OMe group, first you have to choose which one is having more priority. obviously you have to give priority to Cl, because with this carbon number 1, the next atom attached is Cl, here it is oxygen. So next atom you have to consider its atomic mass. Chlorine is having higher atomic mass, so this will have more priority. This is number 1 priority, this is number 2 priority. And in the number 2 carbon you have ethyl group and H, so there you have higher priority groups. So here higher priority groups are on the same side, that is why it is Z. Similarly, here higher priority groups are on the opposite side. So what you have to do whenever you are getting any CC, you are getting any alkene, you just have to predict you have to predict EZ. First focus on left hand side carbon, check the 2 substituents, fix priority. Now consider the second carbon, check the 2 substituents and assign the priority. Now see whether the higher priority groups are on the same side or not, right? Now sometimes they coincide. What I mean, that C's may coincide with Z and trans may coincide with E, but that is not always same. So we will take one example where you will see that C's is not matching with Z. So the molecule will be C's, but it will also be E. So what is this example? The example is, now for this molecule, if you simply consider the idea of cis trans, what you will get? You will see that two similar groups, they are on the same side. So you will be tempted to call it as Z. Sorry, you will be calling it cis. But if you individually see carbon number 1 first, this is higher priority groups. Now separately see carbon number 2. Higher priority group is this one. So now it is basically E. So if you simply consider it C's, it is actually not correct. So it is E here. Now another example I can show you, where suppose instead of H, now you have ethyl group here. And rest of the things I am not changing. Same. Now here again you will see, you will be tempted to call it as C's. But when you consider EZ, now this is having more priority, this is having more priority. So this is Z. And in this case it is Z, as well as, if you want to call it C's, though that is not the right way to do, but Z, C's are coinciding. But in the previous example, Z and C's are not coinciding. It is C's, but it is E. Okay, this is the difference between E and Z. It is not necessary that C's will be always associated with E. There is no such thing, right? Some examples of EZ isomers we will see here. So we'll take some very interesting example, not simple one. So more complex example you will practice, it will be better for you. So here we have this compound. Here we have to call it in terms of EZ, not Cs, because we have more than 2 different groups. We have one cyclobutane with chloro, another cyclobutane with Br, and we have methyl groups. Now don't call it Cs because 2 methyl groups are on the same side. That is not the right way, because you have more than 2 different groups. So considering carbon number 1 first, this will be having more priority. If you simply consider carbon number 1, the next carbon is attached to 3 hydrogen, right? We write it in this way. This type of way that I am writing, same thing you have also seen in the previous unit, unit 12. You can also check it there. What I mean actually when I'm writing something like this. So this carbon is attached to 3 hydrogen. But if you move to the other group, that is the carbon number 1, it is attached to this cyclobutane. It is basically attached to this carbon, and this carbon is attached to CCCl. So it should be CCCl. So that is why this is having more priority. Same logic is also here. This is having more priority. So ultimately, this compound should be Z, right? The next one is Here the double bond is very unique. It will be attached to this cyclopentane ring. Now one side of this we will have CO2 Me group and the other side we will have CH2OH group. Now simply put carbon number 1, carbon number 2. If you look at carbon number 1, there is no separate substituents because the two substituents are attached. But if you move this side, what you get? You get CH2 first, then you get another CH2, then you get methyl substituted CH. But if you move this side, you get CH2 first, then directly you get CCH3. So that is why this side will be having more priority, right? So this side is more priority because you are getting one CH2, another side is 2 CH2. So that is why this side is more priority. What about the carbon number 2? In carbon number 2, obviously it will be having more priority because it is COOMe. Here we have oxygen. So with this carbon, you have HO. But with this carbon, you have total 3 oxygen. Double bond oxygen, we consider it as if it is 2 oxygen. So that is why it is having more priority. So this is more priority, this is more priority, they are opposite to each other. So that is why it should be E. But interestingly, see, if the same molecule I write in a different way. Suppose instead of putting the double bond, try to understand the difference what I am doing. I am not changing the CO2Me group and CH2H group. I am just changing. Now see, this side will be having more priority, isn't it? Because now CH2 I have drawn it in the downward side. So this is having more priority, this is having more priority. So this should be considered as Z. So be very careful whenever you have double bond attached, that is exocyclic. You have some cyclic structure and then external position you have double bonds, you have to name it at E and Z. So you have to do it in this way, right? We have some small time, we'll just finish one more example. Here we have Br, then we have CC double bond. This side we have ethyl group. We have CH2, CH2OH. And here we have, now 2 double bonds we have, but we will just focus on the first double bond which is attached to bromine. We'll try to understand the priority. So if you consider carbon number 1, obviously this is the higher priority, that is easy to understand. But what about carbon number 2? In carbon number 2, if you move from carbon number 2, CH2, CH2, so there will be a tie. Move to the next carbon. With this carbon, you have 2 hydrogen and 1 oxygen. So you can write it like this. Similarly, if you consider this carbon, it is attached to 1 carbon, and here we have C, we have H. So it is CCH. So comparing OHH and CCH, it is winning over CCH because of the oxygen's higher atomic number. So that is why this group will be considered as higher priority, and overall the molecule should be considered as Z. Okay. So 4 very unique examples we have discussed under examples of Z isomers. Next we will also see examples where we will apply nomenclature with some EZ terms. We are ending the session here. Thank you for listening.